We have another arc length formula. There's actually 3 arc length formulas. This is the second one. The first one we will look back at in chapter 7, maybe it's chapter 8, I can't remember, when we go back to that. But so far we've looked at polar length in terms of, arc length in terms of parameters, so parametric arc length. Today we're going to look at polar arc length. So here is the formula. It is on page 245 in your little book. Okay, so whether you want to screenshot that, or I would have your book open anyway because we're going to do example problems from there. If you want to screenshot this formula from your book, great. If you want to write it down, great. And then we'll talk about it and how to deal with it. So just to be clear what's going on here, okay, we're going to be given some polar equation, and we're taking the square root. This is the integral from alpha to beta. So you're going to be given, or you're going to have to find certain angles, right? And so alpha and beta represent some angle measure. And in the problem, it'll say theta equals 0 to theta equals 3 or something like that. And so your alpha is going to be the angle 0, then the angle 3. You're going to plug your r in, and then you're going to have to differentiate with respect to theta, okay? And plug that in. So this is just distance formula, right? A version of the distance formula, another version. You know, square root of something squared plus the other something squared, and go from there, okay? And these are all going to be kind of calculator problems, because you're not going to be able to, I'm sure you can do it. Obviously, it can be done, but trying to integrate these things, by hand is not something. It'd be really painful, let's put it that way. All right, so get this one down. Example 1, find the length of the arc from theta equals 0 to theta equals 2 pi of the curve 2 minus 2 cosine theta. So hopefully the first thing you did was found the derivative. Okay, so the drd theta is just 2 sine theta. Okay, so then the rest is just making sure that you plug it in your calculator correctly. The thing that's important is that you put enough parentheses, because when you have cosine or sine, it's automatically going to give you a left parenthesis, and if you don't add an extra parenthesis in your calculator, you'll just be squaring theta, and then you'll get the wrong answer. So when in doubt, put extra parentheses to make sure, that, because what'll happen is that it should, on your calculator, when you type it in, it should look like that. So that way, the outside parentheses, and you guys are doing programming stuff, that should make sense to you. Okay, that you've got that. And same thing over here. You'll want to have an extra parenthesis to make sure it's not just squaring theta. Okay. And then, right, this is all calculator. So from there, you're punching that in, being real careful. And so, yes, 16 units should have been your answer. All right. Now, I don't know how big a deal it is to put the units on there. They don't tell us what it is. I feel like a problem like this would be a multiple choice kind of thing, so it wouldn't necessarily matter. But anytime you're talking about length or area or volume, eventually we're going to talk about, I think it's important to put some kind of units on there. And I hope that I'm consistent with that, but that's my goal, is to be consistent with that, to always label it, because it has some type of context, okay? All right, so that's the polar arc length. Now let's talk about vectors. And in your book, he crammed it all in there. And so I tried to spread it out a little bit so we had a little more room to write. Of course, you can do whatever you want. But we have this vector over here in the xy plane. And we have to define all these things and make sure that we know how to write them, because especially in 10.5, we're going to apply it. A lot of this stuff today is just sort of just sitting on its own. Doesn't have an application, and then when we get to 10.5, we'll use applications for all this stuff. Okay? So we'll go through these little definitions based off of this and kind of go from there. Okay. All right. So starting off with vectors. A vector is just a line segment with direction, or array. That's what we call it in geometry. Okay. It only is going to go one direction. All right, moving on. The magnitude is defined a couple different ways, and you could see it written one of two ways in terms of symbolism. But here we'll talk about it. Okay. Right. So the other thing to really realize here is that what is the square root of x squared plus y squared in terms of trigonometry? What is this really? Radius. This is r. So since we're talking about polars, that's what we're talking about. So the magnitude is really just r. And in terms of trig, when we learned about unit circle and all that kind of thing initially, that's really what the magnitude is, okay? It could be written, looks like the absolute value with a little arrow indicating it's a vector, or it could have the double wall looking symbols around V is for vector. Okay. The direction has to do with the angle of rotation, right? Because when we started doing this stuff from the beginning, we started off at the x-axis and we started rotating in this case. So this rotation, whichever direction it goes, is just the angle. So we've been talking about this. That direction theta is just the arctangent of y over x. Now, if you're already given the magnitude, or you've already had to find the magnitude, you could use a different trig function. But typically what we do is use the inverse tangent. Okay. All right, so equivalent vectors, I think of a good way to explain this. Think about a vector that has been translated, right? Not a flip, not a stretch, not a smush, but it just slides around to another spot in the grid. That's what an equivalent vector is. It has the same direction and the same magnitude. It's just going to be, it could be in a different place. Okay? It could just be in a different place, just slid around somewhere else. Repositioned, but no turns, no flips, no rotations, no stretches, just same magnitude, so r is the same, and it points in the same direction. Component form is just another way to express the vector, okay? Instead of, as not to confuse it as a point versus a vector, component form like this. Sometimes you'll see it written wider, like taller, not just like a greater than or less than symbol. So sometimes it'll look like this. Right? Those mean the same thing. Okay. Actually, to be honest, I think it's more common to see it this way. I know when I typed it out, I only had so many options, and so that's what I did. Okay. So those are all the definitions that we need to know. Okay, what a vector is, what the magnitude is, it's just r. okay, the direction, and then equivalent vectors. Okay. Any of that new? Have you done that kind of stuff before? Yeah. Not in math though, probably, huh? In science? Did you do this in pre-calc?
Yeah.
Okay. All right, cool. Look at example 2. This one I think I just copy pasted. I don't think I changed anything about it. All right, let's start with A. Let's graph. So this is easy, right? So you put the one point at negative 1, 3, the other one at 2, 7. There they are, very lightly, and then I drew a very perfect arrow. There's A. Part A. Okay. Now, standard position means, what does standard position mean? Yeah, it starts with the origin, correct. Starts with the origin. So we're just going to put it down there. I literally just copy pasted, slid it down. Okay, but what's important to do is, this is where we get into some of these other parts. Find the component form. So the component form of the vector is basically the end point if the initial point is at the origin. So essentially what I'm going to do is I'm going to transform 2, 7. Okay, and so what you have to be able to do is figure out that you have to go right 1 and down 3 to get there. Right 1, down 3, and that's where the origin goes. So if I do the same thing with this, go right 1, okay, and down 3, or you could figure out where this endpoint is. You'd be like, okay, it is at 3, 4. But I like thinking about it, in terms of math a little bit. Right 1, down 3. So in other words, increase this by 1, add 1, subtract 3. So the component form is just 3, 4. And again, that's where this endpoint is, 3, 4. But I think a better way to think about it is what movements need to be made in order to get the initial point of the beginning vector back to 0, 0. Okay. Again, the magnitude is just r. So since I have x and y, it's the square root of 3 squared plus 4 squared, okay, which is 5. Or you can just know the 3, 4, 5. That's okay. And then the direction is going to be this angle. So in this case, we're talking about the arctangent of 4/3, which is 0.927. 3 decimal places. Somebody on the quiz yesterday they decided to round instead of using an exact answer and rounded to like 1 place. Just understand, if you use a decimal ever on the AP exam, 3 places every time. I don't care what the context of the problem is. I don't care any of that. Just put it to 3 places and then you'll always be safe. All right. So yeah, you could also do that for the component. You could subtract the y's, y2 minus y1, x2 minus x1. Yep, that will work too. Because we're just talking about slope. And so the slope of this line and the slope of this line will be the same. So yeah, that will absolutely work. Good suggestion. Last example. Skipping example 3 and going to example 4. Okay. I think I'm going to help you start this one. Do you want me to, or do you want to just try it? You want to just try it? Okay. Just to be clear, if you need this little hint, when we're saying we want the vector in component form, you need to know the x value and the y value. That's what we're trying to find of the vector. So what's important again to remember is that the magnitude is in fact r. And so if we keep that in mind, and since we're talking about polars, keep in mind that, right, x equals r cosine theta and y equals r sine theta. So if I had r and I had an angle, then I could just figure it out, which they do. We have r and we have theta. okay? So in this case, like we said, R is 6, so 6, and then they give us the angle. So in reality, that's all we have to do. Let's figure that out. Which one of these is a half? Yeah, this one's a half. So what's this? Square root of 3 over 2. So x, and actually this one's negative since it's in the second quadrant. And there are my values. X equals -3, y equals 3 root 3. Put in component form, and you're done.
Oh yes, we were. Sorry.
Okay? Questions?